Hello, today we'll be solving problem 3.12, in which we need to find the potential everywhere for two long straight copper pipes, each of radius r, that are held a distance of 2d apart, as shown in figure 3.16 to the right, and one has a potential of v0 and the other negative v0. So the first thing that we'll actually want to do is find the electric field at a distance s from an infinitely long straight wire with a charge density of lambda. And this we can do pretty simply using Gauss's law. So we'll have that the closed integral of E dot dA is going to be equal to E times 2 pi s times our length L, and that's going to be equal to 1 over epsilon naught Q enclosed by our Gaussian surface, which is lambda L over epsilon naught. So therefore, our electric field is going to be equal to lambda over 2 pi epsilon naught s in the s hat direction. And then the potential at a distance s from this infinitely long straight wire will be the negative integral from a to s of lambda over 2 pi epsilon naught s ds. And that's going to be equal to negative lambda over 2 pi epsilon naught ln of s over a. And so here, a is going to be the distance from the wire to the reference point. And now let's consider two infinitely long wires running parallel to the x-axis with uniform charge densities of plus or minus lambda. And this is basically problem 2.52, going back to that. So looking at our diagram, the potential of the positively linear charge density wire will be V plus is equal to negative lambda over 2 pi epsilon naught ln of s plus over a, while the negative linear charge density wire will be equal to positive lambda over 2 pi epsilon naught ln of s minus over a. And then to find the total potential, we can just add these together, and that'll be equal to lambda over 2 pi epsilon naught ln of s minus over a minus lambda over 2 pi epsilon naught ln of s plus over a. And then we can factor out that first part, so we'll have lambda over 2 pi epsilon naught ln of s minus over a minus ln of s plus over a. And so then, using the properties of our natural log, we can say that this is equal to lambda over 2 pi epsilon naught ln of s minus over s plus. So from here, and using this, now let's look at two long straight wires at a distance 2d apart that are now parallel to the z-axis rather than the x-axis as such. So we can see that in the diagram to the left, and our s minus is going to be equal to the square root of x plus a squared plus y squared. And our s plus is going to be equal to the square root of x minus a squared plus y squared. And these are just given by the Pythagorean theorem. So then we can rewrite our total potential as lambda over 2 pi epsilon naught ln of our square root of x plus a squared plus y squared over square root of x minus a squared plus y squared. And then again, using the properties of our natural log, we can just say that this is equal to lambda over now 4 pi, not 2 pi, 4 pi epsilon naught ln of x plus a squared plus y squared over x minus a squared plus y squared. All right, but then from here we do have to figure out what a and lambda are, and actually I am going to highlight this so that we can easily come back to it later because it's a big part of our final answer. All right, so to find out what a and lambda are, for the two wires mentioned above, we can just rewrite this equation as v times 4 pi epsilon naught over lambda is equal to ln of x plus a squared plus y squared over x minus a squared plus y squared. This is helpful because now we can say that our equipotentials will be when we have e to the 4 pi epsilon naught v naught over lambda is equal to our x plus a squared plus y squared over x minus a squared plus y squared, and when these are both a constant, which we can call k. And so by calling that k, we can rewrite this part here as, well, actually, we're going to rewrite this whole equation. And we can say now that x squared plus 2ax plus a squared plus y squared, expanding that, is equal to k times x squared minus 2ax plus a squared plus y squared. And then we can say that x squared, and we can basically pull out our 1 minus k by taking both of these equations on the same side and setting them equal to 0. So we'll have x squared times 1 minus k plus a squared times 1 minus k plus y squared times 1 minus k minus 2ax times 1 plus k, and that's equal to 0. And then we can rewrite this further and just say that x squared plus a squared plus y squared minus 2ax 1 plus k over 1 minus k, right, because we divided everything by our 1 minus k, is equal to 0. And so now it might be helpful actually to compare this to the equation of a circle with its center at x naught, 0, and a radius of r, right? And so that equation would be x minus x naught squared plus y squared equals r, or it could be rewritten as x squared plus y squared plus x naught squared minus r squared minus 2x naught times x is equal to 0. So here then, just by comparing these two, we can see that our equipotentials are circles with x naught is equal to a times k plus 1 over k minus 1, right, from here. So then, and this is when we're applying this back to the problem we're trying to solve, we want when x naught is at d, right, because we want our equipotential to be centered at our distance d from the axis. So here we'll have d is going to be equal to a times e to the 4 pi epsilon naught v naught over x plus 1 over e to the 4 pi epsilon naught v naught over x minus 1, which can be written as a times e to the 2 pi now, 2 pi epsilon naught v naught over x plus e to the negative 2 pi epsilon naught v naught over lambda. And excuse me, this here, that should have been a lambda. So we have that, and then we're going to divide that by our e to the 2 pi epsilon naught v naught over lambda minus e to the negative 2 pi epsilon naught v naught over lambda. And with it rewritten like this, we can see how that would be the hyperbolic cotangent. So we can say that now d is equal to the a times the hyperbolic cotangent of 2 pi epsilon naught v naught over lambda. All right, and I'm going to highlight that so that we can come back to it easily later. We can also say that our a squared is equal to our x naught squared minus r squared when we are comparing our equations to that of a circle centered at x naught 0. So from this equation we can say that r is equal to x naught squared, r squared is equal to x naught squared minus a squared. So then that's equal to a squared, and then plugging in our what we found for x naught, a squared of k plus 1 over k minus 1 squared minus a squared. So then r squared is equal to a squared, and expanding that out, k squared plus 2k plus 1 minus k squared plus 2k plus minus 1, there we go, divided by k minus 1 squared. So then that can just simplify to a squared 4k over k minus 1 squared. Alright, and so then we can just say that r is equal to 2a square root of k over the absolute value of k minus 1. And now we want to rewrite that in terms of our potential v naught. So we can say that r is equal to 2a e to the 1/2, because it's a square root, 1/2 times 4 pi epsilon naught v naught over lambda, and dividing that by our e to the 4 pi epsilon naught v naught over lambda minus 1, and just like before we can rewrite that to be 2a e to the 2 pi epsilon naught v naught over lambda over e to the 2 pi epsilon naught v naught over lambda minus now e to the negative 2 pi epsilon naught v naught over lambda. And then this can just be rewritten as a over our hyperbolic sine of 2 pi epsilon naught v naught over lambda. And then lastly, we can now say that r is equal to a CSC of 2 pi epsilon naught v naught over lambda. And I'm going to highlight that so that we can come back to that. Alright. Now to find lambda, we can simply take our d and our r that we found and just divide them by each other to solve for our lambda. So taking our d and our r, we can say that d over r is going to be equal to our a hyperbolic cotangent of 2 pi epsilon naught v naught over lambda over a, and our hyperbolic cosecant of, and sorry, there should be a h here, because this isn't just cosecant, this is our hyperbolic cosecant of our 2 pi epsilon naught v naught over lambda. Sorry, so to reiterate, we have r is equal to the a times the hyperbolic cosecant of 2 pi epsilon naught v naught over lambda. So then down here, okay, we have a cotangent hyperbolic over 2 pi epsilon naught v naught over lambda over a hyperbolic cosecant of 2 pi epsilon naught v naught over lambda. Sorry about that. All right, and so then that can finally be rewritten as hyperbolic cosine of 2 pi epsilon naught v naught over lambda. And so then, just solving for that, we can find that lambda is equal to 2 pi epsilon naught v naught over our hyperbolic cosine -1 of d over r. And so here, finally, we can say now that this r is our radius of our copper cylinders, or copper pipes. All right, and then also going back up to here, right, we can say, we were saying that a squared was equal to x squared minus r squared, but for our problem we want x naught to go to d, so we can say that a is equal to the square root of d squared minus r squared. And then that allows us to find our final answer. So yeah, here we are, and this a was again just the same from here. So yeah, thank you.